Hello, everybody. So, two subtitles occur to me. You just get both here. I couldn't really pick one. I've got a few things I want to go over in this session. To kick off, though, let's do a little bit into the background. So, I'm Timothy. You might have seen me online in a few places via the name Tekastore. You can see the avatar over there. My background's actually in mathematics and statistics and molecular biology. I'm currently a research assistant at the Telethon Kids Institute in Perth, within a group there which is looking at computational biology. Now, I am a bit of a perpetual tinkerer. As far as I'm concerned, programming ability in many respects is dangerous because it means that when you come across something or a situation where you go, this isn't very good, I think it might be better, I think I could do something about this, and the next thing you know, you've lost hours and hours of your life. So this is a particular project that isn't actually in the course of my work, but was motivated by frustrations that I encountered and done in my own time. Now, I had to look at a lot of data. Dealing with data in an ad hoc way is something I'm sure all very familiar with. It's very tempting, but it's a bit pernicious. You easily go, oh, I'll just download this file, do a few things with it, but then you get asked questions such as, where did you get this from? How do you know it's the same as this file that I've downloaded? What have you done with it? And then those can be quite difficult to answer. So I think what's really needed is a system that's reproducible, robust, reusable, in the sense that you can take, say, one data set that you've been working on in one project and transfer that over to another one. Easy to use. I mean, when don't you want that? And I think really declarative is actually an underappreciated feature. So I was starting off looking at the existing options, having a look here, and I mean, yeah, it gets more complicated from there. If you're starting looking at data, there's a whole mess of formats that you have to encounter and work with. But yeah, things exist. For example, computational pipelines tend to have some degree of data management built in. Kedro probably the standout here, but also SnakeMaker and Nextflow, but it's not really their focus. You've got some Git-based approaches, either built on Git itself or inspired by the design, as DVC is. As well as there's the Python package intake, which is a bit of a data catalog. I actually quite like it. It just doesn't quite do everything in the way that I want it to. And then there's some Julia tools. So artifacts, datasets.jl from Julia Hub, data depths, and a few others. So then I went looking, saw how many of those could I actually find that met the criteria, could be used in the way that I want them to be. And the result was crickets, nothing. So this is the start of the journey, because it occurred to me that there's actually probably a rather strong argument for a Julia native solution to data management. In particular, if you look at a lot of approaches, you sort of do your data pre-processing, cleaning, all of that separately from the analysis. By bringing that all within one Julia project, you actually can capture all of that in sort of a hermetic environment because you've got your project and manifest.toml thanks to how well package.jl works, even for things like when you say, for example, calling binary files. So, for example, whether you be doing, say, I mean, looking at biology, something like SAM tools or some other execution like that, because we have the JLLs, that can also be managed within this environment, which, yeah, makes a rather strong argument, I think. Furthermore, if you've actually got the data sort of pre-processing in the same language that you're actually analyzing it in, I think there's some benefits you can get there. And by having it in the same language, you can now start developing deeper integrations. For example, we've got a custom REPL mode. Now, yeah, so altogether, I think this actually provides a quite compelling set of characteristics. So I think we can sort of raise the sort of high watermark in terms of the reproducibility, combination of reproducibility, flexibility, and convenience that you can actually have. So, several months later, we have DataToolkit.jl, the topic of this talk. Now, just to give a bit of an overview of this, the core idea here is that you can represent a dataset quite nicely as, with a few aspects to it. One is saying that somewhere there exists a pile of bytes, and that is what you're interested in. You need a way of actually accessing that pile of bytes. So this is going from storage to data, and that is the storage transformer. Now, just a pile of bytes by itself isn't interesting. What you really want is a structured representation of those pile of bytes, and that is the information. That's what you actually want to work with. So you have some method of going from that pile of bytes to the structured representation, and then back again, potentially. So that's your sort of loader and writer in this diagram. So this model is what I call a data set, and that's what's captured in this package. Now, this is defined actually, this is actually part of a larger model. So you've got your data sets which have loaders, storage, and writers as actually defining them. And if you have many of those form a data collection. So for example, something like a data collection, you consider like the R datasets package that has a whole collection of datasets. Now you might want to access different data collections at once. So what's actually maintained in the package is a stack. So a collection of data collections, as it were. And I think what's a bit notable here is that some of these sort of deeply nested objects in this diagram can actually access their parents, which allows for a few useful things. Okay, now this model is defined in this DataToolkit base package. We've actually got not just one package, but really a sort of a trio or a sort of four in a sort. So DataToolkit base provides the basic model. It provides a model, but nothing else. It's completely useless as far as actually using it in analysis is concerned. But then we have DataToolkit Common, which does a whole bunch of things like how to actually read a CSV file, image files, and a few other things like that, and provides a number of plugins which are actually rather handy in my opinion. So if you're just doing an analysis project, we've got DataToolkit, which is the sort of user-facing, I guess, package. You pull in that, it'll pull in DataToolkit Common and Base, sprinkle a little bit of nice extras, and you can go ahead and start using that. If you've actually got a collection of data sets that you've put together in a package, you've actually got a Documenter extension which works with the next release of Documenter, and yeah, those are all together documented under one system. And yes, of course, you might also want to pull in those data packages into any particular analysis project you are working on. Okay, so what does this actually look like when you're using it? So we were using TOML files to have a declarative representation of each data set. So in this case, we're starting off, we're going to be looking at or using Fisher's famous iris data set. And so to start off, you just have the data set, you give it a unique identifier, and then you can give it any arbitrary metadata that you want. We define a way of actually getting that collection of bits. So in this case, we say that we can fetch it from the web, and then we have a way of actually loading that into Julia in a way that you can actually work with it. So what's notable here? We've got a named data set. It can be uniquely identified. You can give it arbitrary metadata. There's certain ways of sort of name transformers for loading the data and transforming it into a useful format. We can have things like content verification, and those methods of actually acquiring the data and transforming them into a useful representation can take some number of arguments. Okay, and then what about when you actually want to use this data set? Once you have this representation, we have this rather handy D-string macro, which will just fetch it in the form that you probably want. And so in this case, we've got data frames loaded as well, so it'll get it as that CSV as a data frame. So you can just sum the sepal lengths or something. You can actually also specify particular forms you want by actually including a type in the string. It's not eval, it's actually parse. You might think that's a bit dodgy, but it's actually fairly capable. It gets to about 90% of the way there. For example, you can do some more complex things like actually have type variables. Now, say you've got a whole bunch of data sets, you put them together, you think that it's actually probably going to be useful for more than just you. You might want to make a data package. This is when that Documenter extension I mentioned came in. So if we expand on the iris example from earlier, we can actually generate something like this. Give information, for example, the licensing, the source, the publication it was first seen in, and what formats it's available in. And this is all just nicely generated. You might wonder how much it takes to actually produce something like this. If you use the DataToolkit Documenter package, just add that. Use it in the make.jl file, and then just somewhere have the auto datasets. Yeah, that's it. You'll suddenly have all of the data sets in your collection documented like so. So let's see how this actually might be useful. So this is a basic way of representing data sets. Something else that you're able to do here is actually not just directly use the data set, but actually use it in producing another data set. So I guess you could call it a derived data set. And I think that this is what I found happened quite often in my usage, and was where a lot of tools started becoming quite annoying. So let's say that you have a farm. You've planted a bunch of different types of crops, and you have put some different fertilizers in different fields. And you want to see which fertilizers are actually most effective. So you might start off by having, say, some tabular data giving the layout of the crops and the layout of the fertilizer that you used. You might want to put them together into, say, one table which actually has which fertilizers are used with which crops. So in this case, we've got 3 data sets here, the third one being created by using the first 2. Say then you actually get around to harvesting. You now get crop yields information. That's a new data set. You put that together, crop fertilizers and yields. You've now got it in one tabular form. You look online, you find some information on the fertilizers. That's wonderful. You might write some code to actually incorporate all of that and then, say, make some predictions as to how effective the fertilizers are. So you write a function, and then you have your best fertilizer. So what happens here is we've actually not just done each of these steps incrementally, but captured the entire relation here. What this means is, say that you realize you messed up with your fertilizer layout. You made a mistake there, you correct it. Without doing anything else other than just changing the data that you're using in that fertilizer layout, the change there will just propagate right on through on demand. And so if you combine this with, for example, storage caching or computation caching, this will mean that you just recompute things when needed. Okay, so all of this happens via what I call transformers. So if you go back to that graph from earlier, they're the storage, loader, and writer bits here. The ways of going from a pile of bits to acquiring a pile of bits and going between bits and actually structured information. Implementing them is, in my opinion, dead easy. We have functions for each of them, loaders, writers, and storage, and simply by implementing those functions, they become available to use. So let's actually get some examples. Say that in this TOML file, you just have a value key. All you need to do is say, I'm fetching the value from that. This is just a little macro that's just for convenience. Okay, so this isn't just a toy example. This is the actual implementation we have in DataToolkit Common. Okay, how about JSON then? Well, we've got JSON 3, so we use that, and we just read from the source. Once again, this isn't just a toy example. This is the actual implementation. And then you get the idea. Writing to JSON, we might want to check the pretty parameter, so it's a little bit more complicated. But for the most part, simple things are simple to implement. Right. At the moment, we have 23 loaders, 18 writers, and 6 storage backends. They cover a range of things from images to compression to tabular formats. This is basically just what I found useful. Hope to see other people actually come along with their own loaders for their own data formats that they have to work with. Okay, that's a quick run through the one major component of the system, which is transformers. How you can actually acquire the structured representation of the data that you want using a system which actually allows for declarative representation of your data sets with all sorts of niceties. Now, many of those niceties are actually available via plugins. So there's I think we might call a somewhat sophisticated plugin system here. Why? Okay, a few things. One, I think it's important to allow opting into certain functionality. I don't just want a massive, here's the kitchen sink type approach. Another concern I have here is that certain functionality there might be a bit contentious. There might be different ways you might want to go about one thing. And so I wanted to avoid privileging just one particular approach by baking it into the base package. Finally, I want this system to work for use cases that I have currently not even considered, which are far beyond what I've envisioned. And so for that, I want something which is flexible enough to accommodate beyond what I've currently thought of. Now, you might think, say, a simple plugin system. You've got, say, 1 or 2 well-defined spots where you can plug in to the existing code base and, say, do this first. Just say a list of functions, something like a hook-like approach. I think this is a reasonable expectation. What I've actually found has happened here is that we have a bit of a mess. So each of these circles basically represents a function call where you might want to do something different. Sometimes multiple plugins might want to affect the same function call. A function call of a particular type might be scattered across different parts of the code base. Simply put, it's a bit more complex than actually considering. I have found, I think, the plugin system we want, I think there are quite high demands here, ideally. So modification of multiple places, I've already mentioned. We've also got arbitrary code we want to be executed before and after the function call. Change the arguments of the function and possibly the return value as well. And then I actually want to also be able to prevent or change the function being called. Okay, those are mostly achievable, but then we've got 2 more. I also want this to compose with other modifications and actually also be applied on a per data collection basis, not actually be global. How's this actually done? Well, I think one approach which actually works rather well with this is called aspect-oriented programming. So if you're unfamiliar with this, as I was until I discovered I accidentally implemented it, there are a few terms here: aspects, join points, point cuts, and advice. So put simply, advice are simply modifications that you want to make at a certain point in the code base. Join points are locations, the locations in the code base you might want to modify. And point cuts are ways of identifying this advice, these modifications apply to these locations in the code base. So you can have one bit advice that actually applies multiple places, and you can have multiple advice that apply in one location. Now, how does this actually work? You can sort of think of an advised function call as sort of this function up there. Now, the extra thing that we've got here is actually composable. So if you have multiple advice applying, you basically run through all of the pre-processing steps, so modifying the function and its arguments, take the result, and then run that backwards through all the post-processing steps. Another way that you can think of this is actually having shells of advice built around each other. How does it actually look like in practice? Well, say that when writing to the file system, you actually wanted to create a Git commit every time that you've overwritten the file. So this is a good use case for plugins. What we can do here is say that when we see a write function being called with a file system data writer, and it's written to some path with some information, we define a write commit function, which with the result will actually it'll just pass the result unmodified, but before doing so, we run git reset, git add, and git commit. So we just pass that through in the sort of result tuple, and that will be executed afterwards wherever in the code base that you have these special calls of write. What have these plugins been used for? Okay, so far we have 6 plugins. We have a plugin for actually supporting default values, a plugin for convenient syntax of specifying certain versions of datasets, for actually caching to disk an I/O source, as well as a cache plugin for actually caching the Julia representation, memorizing, so keeping a Julia representation of a dataset alive in memory after accessing it the first time, and then as well one for logging. So this is an example of some of the things that have, or at this point, already been done with plugins. Okay, so if time allows, we have a live demo, and I think we do just about have enough time. So if I pull up a Julia REPL and try to hold the microphone and use the keyboard at the same time, which is a challenge I had not anticipated, I must admit, we'll run Julia 1.10 because it's a bit quicker to load things, and use the DataToolkit package. So what happens here is we can actually, I'm actually going to demonstrate the data REPL and the sort of ease of use part, which I mentioned right back at the start of the presentation. So by typing a closing curly brace, we can enter the data REPL. And let's find some data set that we want to look at. So let's say iris, for example. So I think somewhere Seaborn iris, let's see, CSV, we should find a result here. Okay, yeah, here's a lovely iris CSV. So if we just grab the link to the raw file, let's copy that and say we want to use this. So add iris, and here's the path. Oh, but we actually haven't initialized the data collection. So that's easy enough, we just do init. There we go. Do we want to create a data.toml file for the current project? Yes, we do. Call it live demo, that sounds good. And there we go. So at this point, we can just rerun the existing line. Let's see, Fisher's data. That should work. And then we're done once it's actually run the things. So at this point, all we need to do to use it is just go iris, and we can access that data. Once it's actually run things. So it needs to download the file, of course. And then, we actually need to parse the CSV. So this has a system basically that's the reverse of package extensions. Instead of actually loading code when after loading a certain package, you actually want a certain package when you're using certain functionality. So in this case, we just try to look at the CSV. It's gone, yes, this is a CSV, and it's recognized that, but we don't actually have any packages in this project that can do it. So it asks if we want CSV, and yes, we do. So I'll just have to quickly fetch this and wait for pre-compilation, after which it should just spit out the iris data file. And lovely. Yeah, so this system works rather generally. It's got a few sort of heuristics when you say, I want to add a certain resource, and it would just, all this really does is just generates that data.toml section. So you can accomplish the equivalent result just by going into the data.toml file and typing it out. But I think it's important that with a system that's, I think, got a few of these advantages, like being declarative and having a few sort of guarantees, for example, like checksums for robustness, that you can also be easy to use. And I don't think this is a situation where you have to compromise. I think this, with a bit of extra work, you can actually have both at once. And so the REPL mode here is really for that. It's for the convenience. Okay, it looks like we've now got CSV. And so, yeah, there we go. If you already had the package in the project, you'll see this much faster. And yeah, at this point, we can have a look and do other things, for example, like list the data set. And then there we go, Fisher's iris data. If we had a few other projects, we'd be able to look at the actual data stack, but let's see. Yeah, at the moment, we've just got the live demo you see, which is using the store defaults memorize plugins. And then if we were to, for instance, actually want to look at some of the information, for example, about the plugins or the loaders, that is also accessible within the REPL. We've got, at this point, a fair few sort of handy commands implemented for things like searching from datasets to creating derived datasets. Yeah, there's conveniences for all of these. All right, so let's go back to the presentation. That's just a taster. Yep. Oh yeah, so I can just go back here and just go up to ice, and let's see, there we go. So yeah, once it's loaded, it's there. Also saved to a disk. We actually use the store plugin actually means that if I now disconnect from the Wi-Fi and try to, even in another project, reload this, because it's the same recipe for the iris, it's the same path, the same checksum, or if you actually tell it what the checksum is, it will actually recognize, no, I've actually already got this file. It maintains a cache based on all of the data sets or all of the I/O that you actually want to source, and then garbage collects that as they're no longer used. So yes, that's a sort of deduplication method, I guess you could sort of characterize it as. But yeah, just to finish off this actual talk, I've got some plans at this point. Test, some more tests. So at this point, the base model itself, I think, is actually about 85, 90% test coverage. But DataToolkit base itself is, I think, with these sort of extra functions on top of that, only about half covered. And a lot of work needs to be done with DataToolkit Common and, well, actually, really just DataToolkit Common. Documentation, there's a bunch that already exists, but it's a work in progress. I think I've, at this point, got the sort of bare bones of the user-facing documentation. We've got a tutorial up, but a lot more needs to be done for the actual internals and the other packages like DataToolkit base. Transformers, as you already saw, a bunch exist. Using package artifacts with this seems like a nice thing as a sort of why not. And I think at this point, S3 and GCP are glaring holes, just not things that I've personally used myself. Okay, and then lastly, as mentioned earlier, actually being able to export particular data sets. So if you've got a project where you have, say, I don't know, 20 data sets, you go, I want these 3 in another project, just to have a convenience to take them and everything needed for them to work out into a file. And a related note, I think actually a self-contained combination data.toml, project.toml, manifest.toml. Basically, this is all of the data that I'm using and everything needed to reproduce it in one file. Seems like a nice idea. Haven't explored it yet. Okay, so if this sounded interesting to you, I think I'd love it if you actually have a look at the tutorial, try it out, see if this actually works well for you. We've got the work in progress docs for everything. This is the unified docs mentioned earlier. I think they're fairly easy. So if there's storage and data drivers that you want and you can't see them, please just give them a shot and give me a shout if there's something that isn't documented or you've just got other questions. And lastly, I'm very keen to know what you like or dislike about this system. All right, thank you. Right, we've got one microphone to share.
I just want to pass around the mic, so we have, I think, 3 questions, and it's about enough of 4. So,
yeah. Sorry if I missed this at the beginning. I walked in a little late, but in terms of local storage, are there options to decide like exactly where on the file system that you're going to store everything? Because most of my data sets are way too big to have on the main drive.
The web storage driver that you can just, it doesn't need to download the file, you can just stream the I/O, and possibly I can just provide an I/O stream to whatever. The store plugin that I mentioned, just because I like it, you can dump that to your disk somewhere, and you can set where exactly that is.
I think we should have him have the mic and repeat the question. It's not going to be able to do.
yeah, but do you want to add something more? Or? Yeah, okay.
Give the microphone, so it's going to read the question.
You will repeat the question. Okay.
And I hope you'll get the question and the answer.
Yeah, sure.
Then I'll just shout now. Thank you very much. That was really cool. I'm excited to start using it, and I think you may have just for my PhD I have to write a data management plan. I think you just kind of done that for me. A question I had was, so currently I use artifacts to store anything I generate as part of the package that I build or that I download first and then use as part of the package. Do you envision this package to kind of replace all of that?
It can sort of work with it. So particularly with, I mentioned like an artifact storage backend is something that I see very much working with this. Sorry, the question was, I think, about how this plays with the current use of artifacts, more or less. Yeah. There are other aspects to this. For example, you can actually define multiple storage loaders and just use the first one that actually works. It does a sort of pairing process between the loading and the storage. And so what you could do is, for example, if you actually go through, say particularly in the case of a derived data set, where you actually need to do a number of steps to get to the end result, say they're even computationally intensive, and so you don't want everybody to have to do that who just wants to use the data. What you can actually do is you can take that result, shove it, say, somewhere online, put it in an artifact if it's less than 2 gigabytes, and then actually add that as the first storage backend. And so in that case, you've got simultaneously the just grab it from the artifacts location, easy to use, you don't need to do the whole computation yourself. And then, I don't know, if the artifact server explodes or if you just want to have extra information about it, you also have the full information needed to reproduce the result. Yeah. Is
My question is your package capable of supporting binary formats like, I don't know,
like images?
Could be, or maybe just seismic imaging or something like a binary array that is saved in a binary format is not a text-readable file, right?
Okay, so the question is about support for binary formats as well as textual formats, which makes sense because what I demoed was just a CSV, which is purely textual. Okay, so this isn't really specialized around any type of format. All we say is that there's a pile of bytes somewhere and you want to do something with it. So, for instance, images, which are of course binary formats for the most part, are already supported. And all we do there is we just say, here's a pile of bytes, and then this pile of bytes is an image. That is the loader, just saying this pile of bytes is an image. And so we just pass this, I think, to the appropriate images.jl package to actually get the associated metadata, and so into the appropriate form that you can actually work with it. So I don't really know the details regarding, say, seismic imagery, but on the face of it, I don't see any issues that would pop up. Yep.
Okay, so a common task is like that you load the data set into a bunch of transformation, and then eventually the data becomes something that's completely different than the original data set. So I understand that you understand this problem, but like I don't understand how your package deals with this, like with the, so when you transform data, like does it record automatically what you're doing? And then apart from that, like let's say somebody changed the data set outside of Julia, and then when they load the data, does the package check the hash to make sure that it's actual the data that it expects? And then if it doesn't, does it suggest that we create a new version?
Okay, so the question was about how to actually capture what's done to a data set to create a sort of derived data set, as I've been calling them, and also how I can be sure of the integrity, say, if, say, a file on the disk is actually modified outside of Julia. I think that's basically it. Yeah, okay, so I think it was worth me quickly jumping back to the earlier sort of example diagram I had. Oh, there's quite a few slides. Here we go. So in this case, every box here represents a data set except for the run analysis. So this is a function, and the expectation here is that this would be a pure anonymous function where it transforms the various inputs into your result, and that would be either included raw in the data.toml or in some file somewhere. And so there's a Julia loader that's been implemented, which just goes, okay, I'll just load this anonymous function, run the various inputs through it, and then the result of that function is the loaded form of that data set. And so that's captured within the overall data.toml file. And yeah, which allows that to be just automatically reproduced, for example. So if you had none of the actual computations done here, and you just say, I want the end result, go, okay, to load that, I need to run this function, and then I need these inputs and sort of recursively fetch what's required. Say if a file was edited outside of Julia, that depends on the various checks that are in place for file integrity. So in this case, the way that we check file integrity is either checksum if it's available or the modification time of a file. And this is just with a particular implementation of the file system loader. You could write your own one that took a different approach to this. But that means that if a file is modified, either its checksum will change or the M time will change, depending on whether you chose to track that. And so then that would show up as a change file. And the way that this best fertilized at the end knows that it doesn't need to recompute anything is because it basically does this sort of Merkle tree style hashing on all of its dependencies. So any change anywhere in the sort of DAG that it requires will change the hash, and then it'll go, okay, I need to recompute things, which should ensure that your results are actually up to date with any changes. Feel free to come to me afterwards. I've been basically just tinkering away at this to try to get into a shape which I think is fit to have other people try it. So yes, I'm very keen to hear thoughts on the overall system or any of the specifics. Thank you.